now Clement.
Yeah.
Clement Bera will talk about Fox performance. He's a PhD student at the UK.
Yeah.
Is that right? Also, thank you very much.
Oh, be careful with the table.
Hello everyone. Today I'm going to talk about a project I've been working on with Elliot Miranda for the past 2 years, which is called Sister and which aims to improve the performance of the COG virtual machine. So I work on this project with Elliot Miranda, which has like 30 years of experience in smalltalk virtual machine development. He was working before as a lead architect on the VisualWorks virtual machine for 8 years. And my experience so far, I have worked during 2 years as a virtual machine engineer on Faro, and for the past year I've started a PhD related to just-in-time compiler optimization. Yeah, so just because yesterday people told me you're only working in the virtual machine, you never work in the image. So I also work in the image, and I do things like maintaining the debugging infrastructure or maintaining the bytecode compiler. I mean, that kind of high-level stuff. So COG, if you don't know about it, it's a smalltalk virtual machine, and it's currently the default virtual machine for Faro, for Squeak, for Newspeak, and a few other dialects. So I will first discuss about the architecture of efficient virtual machine, because I don't know if all of you know what is a just-in-time compiler and how it works. Then I will discuss about the goal of the project. I will give an example and go through the example on how the performance is improved. And then I will discuss about our approach and what are our current results. So I assume everyone knows at least that, so that you write as a programmer high-level code like Java or Smalltalk. So I write Java or Smalltalk because the runtime environments are very similar. And basically there is a processor in your computer that understands machine code, and there is something in between that does the translation. So a simple virtual machine works like that. It's you have a bytecode compiler that converts your Smalltalk code to bytecodes, and in the virtual machine there is an interpreter that executes the bytecode, and there is some kind of memory management. So efficient virtual machine adds in addition a just-in-time compiler. So it could be a hybrid runtime like in COG, where you have both an interpreter and a just-in-time compiler, or just the just-in-time compiler like in VisualWorks. And the idea there is that if a method is frequently used, instead of just interpreting the bytecode, you compile the bytecode to machine code and execute that instead, and that leads to better performance. Yeah. So I will discuss a bit how efficient just-in-time compiler like the one of Java's hotspot, the virtual machine provided by Oracle for Java works. All along the talk I will use that example. It's a method display list of drinks, and what it does is that it iterates over a list of drinks and it displays them on screen. So it's basically just a loop. So the portion of code self-display on screen will be executed many times because it's in a loop. The first time it's executed, obviously, as it's a message send, we need to look up the selector display on screen for the class of the receiver, and cache the result of the lookup and interpret the method. The few next execution, we will directly interpret the method because the lookup result is cached. So then, I mean, those numbers, it really depends on virtual machine. In COG, it's usually like the second or third execution of a method. A native code version of the method is compiled. The execution of this version of the machine code version of the method is faster than the bytecode interpretation, but there is some kind of overhead because we needed to generate the native code from the bytecode, and it takes a little bit of time. And so, if the method keeps being executed over and over again, there's usually a third tier in very efficient virtual machine. And what it does here is that basically the virtual machine is enhanced with machine learning skills, and it will look at what it is doing, and it will try to recompile the compile method differently in a way that frequently used cases are faster to execute, and uncommon use cases are maybe slower. And so this kind of adaptive recompilation, it kind of takes a lot of time, so several milliseconds, maybe more. It can be up to 50 milliseconds, so you have to be sure that the method is executed very frequently. So basically, in the Cog virtual machine, we had the first version, so the baseline just-in-time compiler, but we had not done yet the adaptive optimization. So I think in the current, in the modern Smalltalk, there is no virtual machine doing that, but in other languages like Java or JavaScript or C#, there are several languages with such properties. So if we take the example of WebKit, so WebKit is a JavaScript engine for Safari. This is the architecture that they used until 2 years ago. And their tiered architecture work as follows. There is a low-level interpreter that interprets the method for the 6 first execution. Then a baseline JIT compiler compiles the method to machine code. It's quite fast to compile, and the machine code version is used for the 16 next execution. And afterwards, an optimizing JIT compiler recompiles again the method with more efficient machine code. And yeah, so it takes even more time to compile, and it's faster to execute. So in their benchmark, so for example, for the Richards benchmark, the code generated by the baseline JIT compiler was 10 times faster than the interpreter, and the second level of optimization in the JIT compiler added a 3-time performance boost. And basically that's what we were missing in the Cog virtual machine. So the Sista project is exactly that, is to implement the next level of optimization in the just-in-time compiler, and it aims to have some kind of 3 times performance boost. So there are 2 main goals. So one is the Smalltalk performance. Currently, we have some users of the virtual machine that do long computation. So, for example, 3 customers are doing a system on a chip, and I don't really know what they do, but basically they write input, they launch an algorithm, and then they read the result, and the algorithm takes like 4 to 6 hours to run. And if we can make the virtual machine 3 times faster, then it will take 1 or 2 hours, and it will be much better for them. Another aspect is the code readability. So I will explain later why this is important, but the idea is to be able to... the problem if you want performance in Smalltalk right now is that you need to rewrite a compile method in a way that they are faster to execute, and then it decreases the readability of the code. So about the performance, so if we look at the computer language benchmark, so it's not necessarily the most relevant benchmark, but I had to take one. So the latest virtual machine, which is deployed for Squeak on Newspeak, is like between 3 times and 30 times slower than Java 8. So it's like, and it's 40 times slower on things like floating pointer arithmetics and regular expression, and it's like 3 times slower and over benchmark that are related to small integer arithmetics. So yeah, and our goal basically for the Cog virtual machine is to have something like which is around the same performance as Java. So we will necessarily be slower because 3 years ago Oracle said that they had already invested $2 billion in their virtual machine, and we don't have that kind of money. But we would like a VM which is almost as fast and which has, in addition, interesting Smalltalk features like being able to edit the system while it's running, and advanced debugging tools and things like that. Yeah, and about code readability. So the idea, I don't know if you're aware, but some messages are already optimized by the bytecode compiler. So for example, to-do is one of them. When you write to-do in your Smalltalk code, it does not compile to a message send, but it compiles to a for loop like in Java. And the thing is, for performance in the kernel, for example, in the implementation of collections, people overuse to-do and didn't use do because it was important for the performance of the collection. So the way the framework works is that it recompiles on the fly a portion of code frequently used based on the current environment and based on previous execution in order to have a portion of code frequently used faster to execute. So the implementation worked at flow. We announced the baseline JIT compiler with hotspot detection. So hotspot detection means that we will try to detect the portion of code that are frequently used. When it's the case, we ask an optimizer to optimize the method, and then we'll restart the execution with the new method. So here is the example that I will use to explain a bit how the optimization works. So I use the method in smalltalk display, which displays the variable, the list of drinks, and it's basically a loop. And we will assume that in our use case, the list of drink is an array, and it will call this method when it calls the method do, which do 1, 2 self-size do, and a block value. So as I said before, the to do, it looks like a message send, but it's already optimized by the bytecode compiler, and this is basically a for loop. So we will execute that method with over 30,000 different drinks, and we will see how the virtual machine handles it. So the hotspot detector tries to detect compile methods that are frequently used. So the way it works is that the baseline just-in-time compiler adds counters in the machine code, and each time the machine code execution reaches counters, it increases it. And when the counter reaches, well, it's very difficult for me to pronounce that word. So when the counter reaches a threshold, the optimizer is triggered. So the way we designed it is that we added counters and conditional branches. So it was a design choice that was oriented by a paper that was accepted years ago. And the idea behind is that, on the contrary to optimizing just-in-time compiler that had counters at the beginning of each method, branches are 6 times less common than methods in the machine code execution. And in addition, by putting the counters on the branches, we could extract branch information, so basically how many times each branch is taken. So in our example, there is no conditional branch on the first method, so we can detect a hotspot. But in the second method, as the to-do is a for loop, there is a conditional branch that basically exits the loops once it's finished. So here we can detect a hotspot. So we said that we had over 30,000 drinks, so a hotspot will be detected in that method because the conditional jump will have been executed like over a certain number of times, which is currently set to 10,000, I think. So then the optimizer arrives, kicks in, and is like, okay, so this method has stripped. What should I do? What can I optimize? And one thing in Smalltalk is that the block closure evaluation is a very costly operation because you need to create the block closure, which creates at least one object. And you also need to activate it, and you have operation in it like access to remote temporaries that cost and things like that. So the optimizer looks at the current stack. The hotspot is detected on the bottom stack frame, and just over is the stack frame for the method display. So here are the methods we are working with. And what the optimizer figures out is that the block which is evaluated here is in fact created in the stack frame just above. So to be able to optimize the block activation, we need to optimize both the method display and the method do. And this is done by inlining, which replaces a function call by its callee. So we will replace the do message send by the method. Obviously, this is speculative because we take the assumption that a list of drinks is an array, but it may not be an array anymore. So the first thing we do is that there is an optimization already existing in the virtual machine in the baseline JIT compiler, which adds basically a lookup cache at each send site. So we look into that cache, and we try to extract from the cache all the types we have already encountered. And in this case, we will assume that what the virtual machine tells us is that in the 10,000 execution, in all the execution that have been done up until now, the list of drink has been an array. Then we need to add the concept of guard. So a guard is something that checks if a variable has a specific class. So here we will check that the list of drink has effectively the class array, and if the guard succeeds, which means the list of drinks has really the class array, then the execution proceeds. If the guard fails, then the execution stack needs to be dynamically optimized and reuse an optimized version of the method. And if a guard fails many times, then the optimized method is discarded because it's not valid anymore. So the way dynamic optimization works is that we edit the native stack while the program is running. Well, while we interrupt the program and edit the native stack. And so an optimized stack frame, when it's the optimized, it could recreate one stack frame or two stack frame depending on the position in the optimized method. Okay, so now we will go through some optimization paths. So the first one we discussed before is the inlining operation. And so what it does is that it replaces the do message send by the method do, and it adds a guard. So here we can see we have a guard that checks that list of drinks as effectively a class array, and then we have been able to replace the method do by the function. The second thing is that now we have directly a block which is followed by the block evaluation. So this is not needed anymore. So we can inline the block evaluation. And starting from this point, we have removed the block creation, the block evaluation, potentially access to remote temporaries, and everything, all these kind of things. So it also supports inlining block with non-local returns and things like that, but it was too complex to make an example with such case. So then we start to do a bit of primitive optimization. So I will discuss only one, which is the at. So we will try to optimize the at primitive operation. So I don't know if you imagine, but the at operation, when you do object at index in the virtual machine, it's in fact quite complex. So because you need to check is the index, so the argument, a small integer, and if it's not, the primitive fails. Then you need to check is the object an array or a byte array or things like that, and because you need to read a byte or a pointer. Then you need to check if the index is in bounds of the object. So, for example, if you have an array with 3 elements and you ask the 5th element, then the primitive fails and you have an out of bounds exceptions. Then there is also things like if it's not an array but like a block closure, it has variable fields but also an instance variable. So you need to shift the index by a specific number, and you need to unbox the small integer, and well, finally you can answer the value. So it happens that in our case, we have a loop, and we know that the index here is a small integer, that it's in the range of between 1 and the size of list of drink, and we also know that list of drink has the class array because we have a guard before that ensures that property. So we will define an operation unchecked at, and what this operation does is that it assumes that the receiver is a variable size object with no instance variable, and that the argument is an inbounds small integer. Yeah. Well. So there are a few other things that will be done, but I mean you understand the general idea behind the optimization. So now we will discuss a bit about our approach. So the way we design it is that we build the optimizer and the optimizer in the image. They're running in the same runtime as the application. So we enhance the interface between the virtual machine and the image for different reasons like hotspot detection, and then we enhance also the backend. Yeah, so in the image we build an optimizer and the optimizer. So the design we choose is to do a compile method to compile method optimization. and the optimized compile method have access to an extended bytecode set with, for example, unchecked operation and guards. So the virtual machine still have the baseline JIT compiler that converts bytecode to machine code. It's shared between the regular compile method and the optimized compile method. When hotspot is detected, then the optimizer kicks in, it optimizes the method, install it, and when a guard fails, the optimizer kicks in and it deoptimizes and restarts the unoptimized code. So the in-image optimizer, so it takes as an input the current stack with the hot compile method. So it's triggered when the hotspot is detected, and it has access to the active stack. It has also access to branch and type information, so you can ask the virtual machine for each branch and how many times each path has been taken, because that's how we implemented hotspot detection. It has access to type information for each message sent, because it can ask the virtual machine for each inline cache what are the types that it has already met. And what the optimizer does is that it generates and installs an optimized compile method. This compile method is associated with metadata that is used mainly for the optimization. Yep. So the critical optimization we have implemented so far are inlining of method enclosure, specialized version of at and output, specialized arithmetic, so it's mainly used in loops like to increment like plus or less or equal. And yeah, there is a few other details, but yeah, we'll not. So what the deoptimizer does is when a guard fails is that it has the stack to deoptimize. Yeah, so I talk about failing guard, but it can also happen that you interrupt the program, you want to open the debugger. So at each point that a method can be interrupted, you need to keep the optimization metadata. And so typically the optimization is triggered by a failing guard, but it can also be triggered by the debugger. And so it used the stack, the bottom stack frame and the optimization metadata to generate the optimized stack to an optimized stack, and potentially discards the optimized method if it has been several times that the guard has failed. So yeah, we designed the optimizer and the optimizer in Smalltalk. It's running in the same runtime as the application. So we choose to do that because our virtual machine is written currently in Slang, which is some kind of restrictive Smalltalk that compiles to C. So for us, it has advantages over C, but it's still very close to C, and it was very difficult to us to implement such an artifact. And it's easier for us to debug and program in Smalltalk. It also allows us to edit the optimizer while the program is running and things like that. And we believe that by doing it in Smalltalk instead of C, we will lower the engineering cost. Yeah. Assuming people are more efficient in Smalltalk than in C. Yeah, so one very interesting property of Smalltalk is that, I don't know if everyone is aware, but you can access the stack frame in the form of context, and you can do everything like setting the sender of a context and things like that. And all this infrastructure was already implemented in the virtual machine. And it was already used for things like continuation, exception, and debugging. So we could directly reuse that to edit the stack. Yeah, so we had a few issues with this design of putting the optimizer in the optimizer in the image. So yeah, one is that currently the user can see the optimized context. So when you do this context and you inspect it, you can have potentially a context with an optimized method. So if it's the case, it's necessary at an interrupt one, so you can ask the context to deoptimize itself. But yeah, it's still possible to see it. And the debugger has to be aware of optimized context and things like compile method. They have to be aware that they can be optimized so that the IDE will show correctly the method and things like that. So there is a bit of IDE integration. The main issue is also these tools. What if the optimizer is triggered while optimizing? So it's running in the same runtime that the Smalltalk application. So it could be that the code used by the optimizer will trigger optimizer itself. And the other problem is that what if the optimizer requires itself to de-optimize some method? So the first problem was quite easy to solve. So once triggered, when a hotspot is detected, the virtual machine does a callback in the image that triggers the optimizer. Once it's triggered, the callback is removed from the virtual machine, so it can't happen anymore, and it's restored when the optimization is finished. So theoretically, it means that the optimizer cannot optimize itself, but we will discuss later how we can do it. Yeah, so it cannot optimize itself, but the thing is that as we are editing a compile method and installing them in classes, when we do a snapshot, so when we save the image, we save the optimized compile method. So it's possible like to ship the application pre-heated and do not have some warm-up time. And this way it's possible to pre-heat the optimizer. Yeah, so this was one of the main issues. We discovered it very late. So actually I had the bug, I was debugging it, and yeah, we had not think about it before. So it can happen that the dynamic de-optimizer, while de-optimizing, requires to dynamically de-optimize the method it uses. So we had no good solution for that for now. So the way we do it is that we swap the runtime to a stable state, and for now it's a bit of a hack, but I keep 2 arrays of method dictionaries, and one has the method dictionaries with the optimized method, and the other one has method dictionary only with unoptimized method. And so as the become operation is now very fast on the Spore virtual machine, we can just become all the method dictionary in like 20 microseconds, and then we need to flush some cache in the virtual machine, like the lookup cache, so they do not still target the optimized method, and we can perform the dynamic de-optimization. So this de-optimization part is quite uncommon, so it's very rare, but well, it's still a problem in my opinion. Yeah, so as I discussed before, as it's a compiled method to compile method optimizer, the snapshot saves the compile method, so it's possible to ship the application in a hot state and all this kind of thing. Okay, so the second part we worked on, it was to extend the interface between the virtual machine and the image. So the first thing was to extend the bytecode set to support unsafe operation and guards. The second thing was to add an introspection primitive on the compile method to extract type information on message sends and branch information. And lastly, we added a virtual machine callbacks to trigger the optimizer and the de-optimizer. So we still allow become. So the thing is that there is it's a complex solution, so I can explain it. But so one thing is that we decided to so that's why we're reintroducing the write barrier. We want the literals basically to have a write barrier, so you cannot become the literals without requesting dynamic de-optimization of specific methods that uses the literals. So that's one thing. So in order to be able to assume that literals are constant, right? The other thing is that it's for temporary variables in the method. So the way become is designed in the Spore virtual machine, it requires a stack zone scan, right, to check if the receiver now points to a forwarding object. And so in this stack zone scan, you need to scan the temporary variables of the stack frame that has an optimized method. Sorry?
I don't think there was a temporary variable for the receiver of you in the dreams example.
Yeah. So list of drinks is an argument. So it's it's not temporary variable, but it's in the same.
Supposing there is a self something, whatever, like self list of drinks do this. Now if there's no temporary variable, it's not an argument. So suppose that they decide that do we go become that. And one could do it.
Yeah. Yeah, but the value has already been pushed and well, I mean, we can discuss about it later. So there is lots of details, like for example for dart collection, because it iterates on an array which is an instance variable, and there are multiple tricks. But
I have a similar question on the same slide. First, the receiver is in the context, so if you have it saved and you are detecting what the stack is the receiver. Then I have a question. I don't know if you've thought about it. Maybe yes, I have a solution, or maybe not yet. But on a multi-threaded environment, even if it's green threads, when you do the unchecked add, that's very dangerous because you might break the VM, not the process. Like.
So the VM is currently single-threaded, so I mean there's support for multi-threading, but with a global interpreter lock, so there can be one thread at a time currently at most that accesses that part. So.
But still, even if it's green threads there is a check to see if you need to reschedule the task in case the to-do is too long, even if it's green threads.
Yeah.
So you might switch to another task that changes the length of the.
Yeah. Okay.
The collection. So that's a memory. That's a map.
That changed. So, how can you change the length of an object before it become?
Well, it could become, for example, if it's just a simple array, you cannot do it. But
so yeah.
I guess this was just more general than just an array.
So basically, there is very few. Yeah, there is very few operations that can do that, like become and their catch. So yeah. And
only for array.
So basically, there are two operations that we consider uncommon that are handled specifically. It's become and context stores. So you could also do like this context sender receiver and set something there. And these operations are catch and requires the optimization. And I don't think you can change the length of the object else. But yeah, so I was discussing about the extended bytecode set. So we extended it with guards and specialized inline primitives. We wrote a paper about it at Isuga, I think 2 years ago. So we also added an introspection primitive. So it's a compile method and it answers type information for each message send, branch information for each conditional jumps. It answers nothing if the method is not in the machine code zone. So the virtual machine callback we added were very similar to does not understand. So it's a selector and the special object array. The message is sent to the active context when an hotspot or guard failure is detected. Yeah, so here are some discussion about the interface. So the way we design it, every change to the interface has some cost. So we had to keep the interface as small as possible. And it can constrain a bit the optimization because everything that cannot be encoded in the bytecode set is kind of lost information. So for example, in the add primitive, we have two unchecked operations, one for pointer object and one for byte object. But yeah, so if the compiler can ensure that the argument is a small integer but not an inbound small integer, for example, we cannot use the specialized operation. So there are details like that are a bit problematic. The other one is that right now we do not manage boxing and unboxing of small integers from the image. If we do, it multiplies by 2 the number of primitives because we need to have them between a small integer and box small integer. Yeah, so the other thing is that the bytecode is currently stack based. We didn't change it to be able to reuse the backend, but the problem is that the image optimizer converts the bytecode in some kind of tree address code representation, and then it has to convert it back to a stack-based representation, and then the JIT backend converts it back to a tree address code representation, so it's a bit redundant. Yeah. Tree address code. Tree address code. What? Three, like three? Address? Okay. Sorry, see, it's my English. Yeah, so then we had to extend the existing JIT compiler that was doing the conversion from bytecode to machine code. So one thing we had to add is the support for the new bytecode operation. Then we added the introspection primitive and the virtual machine callbacks. So the inline primitive were fairly easy to add. It's usually a few machine code instructions. So for example, for @, so you remember this is conceptually the implementation. So this is the method that generates the @, primitive in the Spore virtual machine, which is already simpler than the version before. So it's 145 line. And like basically unchecked pointer @, for example, in 64 bits is just unbox the argument and then do a memory read on Intel. So it's like 2 lines of code to generate the operation. So I still wrote some tests to ensure that all the inline primitives were working fine, but yeah, it was fairly easy. So the only operation that was a bit more difficult was the guard. There are multiple cases with immediate object, things like that. And the problem is that we didn't design it right at first. So what we did at first is that at the guard position, we will jump over a call to the callback in the runtime. And that was a problem because if we have several guards in a row, the machine code, when the machine code is executed, it jumps a lot. And so, well, we had some performance problem there, and the way we changed it is that we changed the guard to jump to the end of the machine code method, and put the callback to the runtime there, and well, I don't know, it was slightly faster, but yeah. So yeah, due to the fact that we changed the design, it was a bit more complex to implement. So the introspection primitive, so I guess it's a lot of work, but it's not me who implemented it, it's Clement. And yeah, basically it reads the inline cache and the counters value, and it answers arrays of array because it was very convenient in the virtual machine to create only arrays. Yeah, and the VM callback, as we discussed before, it's implemented similarly to the does not understand callback, so all the infrastructure was already there to implement such callbacks. Okay, so another problem we had was to improve register allocation. So an unoptimized method we had very low register pressure because Smalltalk is mainly composed of message send, and you have to be able to open the debugger at each message send. So you have to split every register at each send, and so basically you can optimize the register just between 2 send, and there is almost nothing there. An optimized method, the register pressure was much higher. So the existing version we had is that to allocate a register, we would allocate them by abstract name. So we have some kind of domain-specific language with that abstracts from the different assembly code we support, like ARM, x86, MIPS. And so, for example, we have a register we call receiver register, and it maps to EDX in x86, but it maps to R1 in ARM and things like that. And so when we will allocate a register, we will always say, okay, allocate the register name receiver register. And we needed to add the possibility to allocate basically a register that is, to analyze which register are used and allocate a register that is free. So in an optimized method, the register pressure is low. And the thing is that we have many routines such as trampoline, or we have also calling convention for message send. So it means for message send, for example, the receiver and the arguments needs to be in specific registers. So that's why allocating register by name was made a lot of sense. But in optimized method, there is much more. There is a lot of inline primitive next to each other, and so the register pressure is higher. There is fewer routines and sends, and so yeah, we had to change a bit the register allocation logic. So the only thing we have not done yet is to save register state across branches. So yeah, so the problem is that right now when there is a branch, we spill all the values, and in some cases, like now as we discussed, guards are conditional jump to the end of the machine code zone, and yeah, it implied that there is a lot of spills around guards, and it's a problem because it's a lot of memory write, memory read. Okay, so about the stability. So we consider we have low engineering resource compared to other virtual machine like Java. We have no 60 people, but more like 2, 3, 4 people, or something like that. We do not have either thousands of human testers, but no. So what we were doing is using a continuous integration server to run benchmarks and to run test suites. So one important thing we changed is to layer the test suites. So the idea is that at each commit, the continuous integration server automatically runs the test. But in compiler tests, you can do things like take all the compile methods of the system and do different analysis on it. And the problem is that, for example, the test on dynamic optimization, it takes 8 days on a single processor. So I cannot wait 8 days after each commit that the test finish. So I run them like once a week, and I try to speed them on 4 slaves, on several slaves. So basically, the idea here was to layer the test suite and say, okay, we have a basic test that takes a few minutes to run, and then we have test that takes a few hours, and then we have test that takes a few days. When one layer is finished, it triggers the next layer. And yeah, we can keep developing once the first layer is finished, and we have the information later if we break something that breaks the tests that are longer to run. So right now it works. Most of the features are there. It's quite unstable. The bugs are almost only in dynamic optimization, and so yeah. So some benchmark finished. So what I call micro benchmark is things like we add in the computer language benchmarks. And about macro benchmarks, it depends. So sometimes they finish, some of them finish, some of them crash in dynamic optimization. It's difficult. So it's usually bugs in the metadata which is used to restore the unoptimized stack. So the hotspot detection. So we tried with the Richards benchmark, for example, and the hotspot detection was like a 3% overhead on that benchmark. So there are other benchmarks with a lot of conditional jumps. Especially a lot of on of or successfully, where we can see an override of like the benchmark gets twice slower. So we have not fixed that yet. But currently, with adding the hotspot detection at 3% override on most benchmark, or 3 to 5, and it allows us to detect hotspots and to have branch counts. So basically, to know how many times each path of a branch is taken. So yeah, so the current benchmark, so it's mostly micro benchmarks. Up until now, we were fixing stability. We were not looking for performance, so it does not mean much, but yeah. So for example, on the benchmark from the language game, the language game, or on Fibonacci and things like that, we are running currently on an average of 1.5 times faster than the current virtual machine. So it looks good because, for example, when the JIT compiler was started, the first version was actually running slower than the interpreter, and after tuning it, it got faster. And so, for example, I had one benchmark, trade rings. It was actually twice slower once the optimizer was there, and after I changed a few settings in the optimizer, it got like almost twice faster. So there is many settings everywhere in the compiler, in the optimizing compiler to change. So yeah. About the ID integration, so when you do things like speculative inlining, you need to remember dependencies. So the way we did it is selector based. So if we inline a method, we keep in the dependency map at its selector the list of optimized methods that have inline a method with such a selector. And when we install a method with that selector, we need to discard all the optimized method, because it can happen that the lookup result that we have inline has changed or things like that. So methods are discarded lazily. So yeah, so currently the way we do it is that we ask the virtual machine to convert all machine code frames with the optimized method to discard to interpreted frames, and we change the bytecode to only the guard failure bytecode. So that basically when the execution will resume to that method, it will directly trigger the optimization. And the stack frames that are in the middle of the stack are necessarily at an interrupt point, so there is metadata for the optimization. Yeah, so we would like to change that to the way it was done in the self virtual machine to change all interrupt points in the machine code to a call to a routine that triggers dynamic optimization. But, yeah, so about the IDE integration, so the class browser looks like it works fairly well, so we can install new method and it correctly discards the correct optimized method. It also do not show currently the optimized method because you do not want to see that, you want only to see the regular code. So the debugger, there is still work to do. So every context can currently be optimized at each interrupt point, so each message sent, each back jump. So it's possible to build a debugger on top of that, but it's not done. Yeah, so now we are working on stabilization, on tuning the performance, and on IDE integration. Yeah, so I'd like to thank my supervisor, Stefan Dikas and Marcus Denker. I'd like to thank Ryan McNack, which is working on, he is working on the Dart virtual machine at Google, and he does a lot of review of what we do, and also Yaron Kashai, which is the boss of Elliot and allows us to do that project. Yeah, well, so we are stabilizing the system to run more benchmarks, and yeah, we hope to go to production at some point, but so it really depends on what customers want to fund first or things like that. So, questions? Yeah.
Can you run this consideration vitals on architecture for which you do not have an active code generator? And is the vital consideration separated from the active code generator?
Yeah. So the two operations are completely separated. So the thing is that right now, the way it's designed, the unchecked operation used by the optimized compile method are very efficient in machine code because we extended the bytecode to support them. And the interpretation, so we have also an interpreter version of each unsafe operation because it happens on an uncommon case that an optimized method will be in an interpreted stack frame. So it's possible, but it's not optimized in that direction. So we optimized for the JIT compiler. So, for example, if you would run the optimizer with only an interpreter, I am not sure you would earn performance. But it's definitely possible to do tuning in that direction. Yeah. Well, it depends on how you implement the unsafe operation. Yeah.
In one of your first slides, you showed that sometimes I think it was VA was 30 times slower than Java.
Yeah.
Do you know which cases?
Yeah. So the two cases are regular expression benchmark and floating pointer intensive benchmark. Yeah. Hardly, but so this is common compiler technology, so it's done similarly than in in the crankshaft optimizer for V8, which is the JavaScript engine for Google Chrome. And so basically the bytecode is converted in some kind of control flow graph, which has the single static assignment property. And then based on that, you can analyze the range and propagate them. And it's done based on a paper which is called something like ABCD. So I took that algorithm, and basically I compute ranges, and based on the ranges, I optimize the at operation. That was your question?
Do you decompile the native version?
No. I start from the byte-coded version, but I map the information from the machine version, like the type information from the inline cache and the branch information. Yeah.
So when you replace a method with language for optimization, you change the stack, right? So you run one thing and you debug another thing. Because as I understood you, when you debug, you go back to the normal method.
Yeah.
So my question is, isn't this having an impact on your debugging activity, or you have a way to debug what is being executed?
So for the programmer?
For you, I mean.
For me?
For
Okay.
You, yes, because you said there are things that are not working as expected.
Wow. So I'd say not really. Yeah. So I can debug that from the virtual machine simulator, and it uses a processor simulator, so it simulates the processor. I can do such things, but I didn't build any specific subclass of the debugger that would be able to step over optimize the method. Maybe it would make sense. I don't know. Yeah.
Have you considered a queue of methods to optimize?
Yeah. So
One by one, and then you turn off the callback feature.
yeah. So we've okay. So we're still turning off the callback currently. So the scheme you describe, I think it's used in the Graal compiler of Java Hotspot. So the problem is that we have a limited amount of time to optimize the compile method. So what we do right now is that if within like for example, I think currently it's 50 milliseconds, the optimize method was not generated, then the optimization process is postponed to a background process, which has a queue. But the problem if you do a queue the way you describe is that you have either to add element to the queue from the virtual machine, or if you add them from the language, then you will end up again with the metacircular problems. No? I mean, if you have a queue in the language, it means when you add element to the queue, it could trigger the optimizer, and then you have an infinite loop. And